Welcome back to another video, 6.3. We are talking about applying the method of cylindrical shells to more general solids of revolution. So as I mentioned in a previous video, this video is going to be a lot more example driven. And let's just dive right in. In this example, we're looking for the volume of the solid of revolution generated by the region bounded by y equals 4x minus x squared and y equals x about the y-axis. So to understand this, I drew already the region in the plane that we're talking about. Now, y equals 4x minus x squared, that's a parabola that opens downward, and y equals x is a straight line through the origin. And the region between them, the area between the two curves does not touch the x-axis, so we're going to have to readjust the height calculation, but it's not that big of a deal. We're just going to subtract, we're just going to actually take the area between the two curves calculation and adjust it slightly. But first we need to find out the points of intersection. So we know that the left endpoint is 0, but what's the right endpoint? Well, if we set the two curves equal to each other, then we should get a polynomial equation that we can solve. We end up with 0 equals 3x minus x squared, which if you factor out the x gives you x and x minus 3 as the two linear terms. And then by the zero factor property, we know that x will either be 0 or 3. And that gives us our two endpoints. Now, when we're setting up the infinitesimal shell, remember that we're looking at a thickness of dx. The height in this case is going to be the upper curve minus the lower curve. So it's going to be 4x minus x squared minus x. And lastly, the radius slash the rotation factor gives us a 2 pi x, and that's every time. All right, then the volume is going to be the integral from 0 to 3 of 2 pi x times 4x minus x squared minus x dx. So that'll reduce down to the integral from 0 to 3 of 2 pi x 3x minus x squared dx. And if we factor in that x, then we'll just end up with something polynomial. So I'll factor out that 2 pi. And now we're looking at the integral from 0 to 3 of 3x squared minus x cubed dx. And now we integrate. We're looking at 3x squared is going to have an antiderivative of x cubed. And then x cubed becomes x to the 4th over 4. And it's going to be from 0 to 3. So we'll continue this on another page. If you notice, the plugging in 0 is not going to contribute anything, so we can just evaluate it at 3. This volume is going to be 2 pi times 27 minus 81 over 4. And then with some fraction arithmetic, we get that this is 2 pi times 27 over 4. And so finally, this is 27 pi over 2, and that is the integral. Okay, not too bad. All right, let's do another example. So in this case, now we're going to revolve around the x-axis. And what this does is it's just going to make it so that we are going to need to express everything in terms of y. So as usual, let's set up the problem. What is our region bounded by? we have y equals x to the 3 halves, y equals 8, and x equals 0, and we're revolving it about the x-axis. So let's draw in the picture here. So roughly this looks like this curve right here. And it is bounded by this upper curve here. So that's 8 right there. But if we express this in terms of y instead, then all we need to do is apply the opposite power. So 3 halves gets canceled by 2 halves, which means that this equation can also be expressed as x equals y to the 2/3. And the bounds are determined by, we know that y ranges between 0 and 8. So our infinitesimal shells, they actually are going to end up looking like this. So they're horizontal now. So per usual, the thickness is dy. The height now is going to be y to the 2/3. And we are bounding it between 0 and 8. So our integral becomes volume is the integral from 0 to 8 of 2 pi y times y to the 2/3 dy. And again, this is going to end up being some power of y. So if we pull out the 2 pi, we just have the integral from 0 to 8 of y to the 5/3, because that's a y to the 1 power, and that's a property of exponents. Then, integrating that, we get 2 pi times 3/8 y to the 8/3 from 0 to 8. And again, the 0 doesn't contribute anything, so we just need to plug in 8. And so we get 2 pi times 3/8 times, and then 8 to the 8/3. You can confirm independently that this is going to be 256. And then when you simplify all this, it becomes 192 pi. So the only real difference here was when you set up the integral. Remember that in this case, revolution about the x-axis is going to force you to convert everything in terms of y. Okay, let's keep moving. In another example here, we're going to integrate where we have an arbitrary axis parallel to the y-axis. This is going to change how we evaluate the radius of the shells. And so for this one, we're gonna take this a little bit slower. So just for the sake of, let's see, the region that we're talking about here. So the region is bounded by y equals 2 square root of x minus 1 and y equals x minus 1 about the line x equals 6. Okay, so now I'll draw that region. So the axis of rotation here that I want to draw in, I'm going to represent that as this dashed dotted line. And the actual curve then is going to look something like this. Oops, that's not right. It'll look more like this. So the upper curve here is y equals 2 square root of x minus 1. And the lower curve here is y equals x minus 1. And now if we think about our infinitesimal shells, let's be careful here. So our infinitesimal shells, they're still going to have a thickness of dx, okay? But they're being rotated all the way around this line. So the distance that actually defines this radius is distance from this arbitrary axis. So that means when we set up the infinitesimal volume, we're going to multiply by, so we're going to have 2 pi 6 minus x, because we're talking about distance from the x equals 6 line, and then the difference between the upper curves and the lower curves, and then dx. And again, our lower curve is x minus 1, and our upper curve is 2 square root of x minus 1. So what this actually ends up looking like after we set up our, after we find the points of intersection, since we need the endpoints. So we're going to set these two equal to each other. So 2 square root of x minus 1 equals x minus 1. This is actually just a radical equation. So square both sides, you get 4 x minus 1 equals x minus 1 squared. And if you multiply that all out, that's 4x minus 4 equals x squared minus 2x plus 1. Move everything over to one side. So 0 equals x squared minus 6x plus 5. Factor that and you get x plus 1. No, they're both negative. Minus 1, x minus 5. And so x is going to be 1 and 5. So those are our left and right endpoints respectively, which means the volume integral is going to be the integral from 1 to 5 of 2 pi 6 minus x times 2 square root of x minus 1 minus x minus 1 dx. So this feels like it should be a pretty substantially long integral, but it's not going to be too bad, just as long as you follow your notes. Okay, so what we're going to do first is we're going to simplify everything inside the larger set of parentheses. So don't change anything yet about the first part here. I'm just going to distribute that negative sign so that we can see very clearly what is the second set of parentheses. All right, so now we're down to a polynomial-like multiplication. Okay, so we're going to multiply this expression by this expression, and so we'll end up with an assortment of different terms. All right, we're going to need more space for this. So let's go ahead and keep going. Integral from 1 to 5 of 2 pi. And then here, now we can do the, actually I'm not going to use brackets because I use brackets for a very specific thing here. I'm just going to use a large set of parentheses. So you can do distributive property or set up a table to multiply this all out, but you should get 12 square root of x minus 1 minus 2x square root of x minus 1 minus 6x plus x squared plus 6 minus x dx. Okay. So this piece right here, this is all polynomial. We can clean it up, but it shouldn't be too bad. Now, this right here will require the use of the substitution rule, but it also won't be too bad. The one that is actually going to be the most confusing is this one right here. What do we do with this? So let's do an aside, okay? And I'm going to highlight these two pieces. So let's call this integral 1, integral 2, I'm using Roman numerals here, and integral 3. So integral 3, that one's the least concerning of them all because we know how to integrate a polynomial. But let's start with integral 1. So for integral 1, okay, we're looking at what does the integral of, and we can worry about the 12 or not worry about the 12. For our sakes, let's forget about the 12. What's the square root, what is the integral of the square root of x minus 1? Well, we said the substitution rule should work here. If we let u equals x minus 1, then du will just be dx. And when we plug it back in, that means that the integral becomes the square root of u times du, which of course is u to the 1/2 times du. And so if you use the power rule, then it's not too bad, right? The power will become a 3/2 because you add 1. So u to the 3/2 over 3/2. But we don't like complex fractions, so we might as well just write that as 2/3 times u to the 3/2 plus c. Now in our case, we have a definite integral. We don't care about the plus c part, but for completeness sake, we should include it. All right, so that takes care of the first integral. As for 2, we are talking about the integral x square root of x minus 1 dx. And how do we deal with this one? This one is going to use the same substitution, actually, because if we let u equals x minus 1, and again, du equals dx, so that also is nice. We can solve this first relationship for x. So in other words, double-sided arrow here because it's interchangeable. We're not actually, we can go backwards. X equals u plus 1. So wherever we see x, we're going to replace that with u plus 1. In other words, the integral becomes u plus 1 times the square root of u du. And that's not bad, because that's the integral of u times the square root of u. So u times u to the 1/2 plus u to the 1/2 du. And if you use the product rule, not the product rule, if you use the power rule and recognize that this becomes u to the 3/2, so that's going to be 2/5 u to the 5/2 plus 2/3 u to the 3/2 plus some other constant of integration that, again, we're not going to care about. All right, so that was a lot of work, but okay, let's go ahead and split this up then, because the third integral, again, is not going to be too much of a big deal. Remember that the third integral, if I have enough room here, the integral of, and if we combine like terms, right, this should actually end up being x squared minus 7x plus 6. And that's going to be x cubed over 3 minus 7x squared over 2 plus 6x plus some other constant of integration that, again, we do not care about. All right, it's time to put it all together. Okay, so continuing our work here, the volume integral is going to be 2 pi times 12 times 2/3 u to the 3/2 minus 2 times 2/5 u to the 5/2 plus 2/3 u to the 3/2 plus x cubed over 3 minus 7x squared over 2 plus 6x. And remember that this is going to be evaluated for x equals 1 and x equals 5, and we still have that trace of u. So after we clean up the algebra here for u, then we're going to replace back the substitution, which is 2 pi times, and here we have two u terms that have a power of 3/2 and a u term that has a power of 5/2. So I'll put that first. It's going to be negative 4/5 u to the 5/2. And then combining the other two terms, I'm going to end up with plus 20/3 u to the 3/2 plus the rest of the polynomial part here. So what is that going to be? It's going to be plus x cubed over 3 minus 7x squared over 2 plus 6x, and again evaluated from x equals 1 to x equals 5. And now I'm going to replace back u because we should express everything in terms of x. So negative 4/5 x minus 1 to the 5/2 plus 20 over 3 x minus 1 to the 3/2. I'm going to continue down on this line down here because I'm running out of room. And now it makes sense. Everything's in terms of x and we have no trace of u anymore. So now all it takes is evaluate everything, right? But the nice thing here is that when you are using FTC2, so carefully write everything out, but notice that when you plug in 1, the first two terms here, so here's term 1, here's term 2, these two terms are going to go away when you plug in 1, so you don't have to worry about them for that. And so, if you carefully follow along and plug in everything correctly, you should get 2 pi times negative 4/5 times 4 to the 5/2 plus 20 over 3 times 4 to the 3/2 plus 125 over 3 minus 175 over 2 plus 30 minus 2 pi 1/3 minus 7/2 plus 6. And then if we insert some tedious algebra here, fill it in yourself, we should end up with 272 pi over 15. And that is our answer. And lastly, I just want to show you how to set up this last kind of integral that has to do with shell method. There's just a catch here with this one, and I won't reveal the surprise yet. So again, the trick here is that we are talking about an arbitrary axis parallel now to the x-axis, and we're gonna rotate about that axis. So our region, is bounded by x equals the square root of sine y for y between 0 and pi, bounded by x equals 0 and about the line y equals 4. So to give you a picture of this scenario, so I'm going to fill in this line y equals 4. This is our axis of revolution. And specifically, our only piece here that we're talking about for this function is going to look something like this. So this is x equals square root of sine y. Feel free to graph this yourself if you'd like, just to verify that this is what it looks like. So just to clarify, this is 4, here's pi, here's 0. And so when we rotate around this line, that means our shells are going to be these infinitesimal shells laid horizontally like this. So as we set up the infinitesimal shell, right, our thickness is dy, and the radius of such a shell is the distance from the line 4, okay? So it's going to be 4 minus y, because 4 is greater than y in this case, right? And we want this to be a positive distance. And so this means that when we set up our integral, we're looking at the integral from 0 to pi of 2 pi 4 minus y square root of sine y dy. Except we have to stop here because we don't know how to evaluate this integral yet. So the first one, so notice that the real stickler here is this term right here, square root of sine y. So it's nested, which means we would need like a reverse chain rule here. And we don't have something like that. So hopefully this is a good glance ahead opportunity to chapter 7, where we develop new integration techniques that are going to actually allow us to tackle problems like this. Okay, and so that concludes section 6.3. All the integrations here, they follow the same kind of format as the previous section. Just remember that in this case, the infinitesimal slice is no longer literally a slice, it's going to be a shell. So that's the real main difference here. In the next video, we're going to move on to the next section, 6.4.